computer. Okay, so as this section and my other section as a whole, I just did a look at the grades as they are right now with all the homeworks and but only those 4 grades missing. And there's 11 A's, 55 B's, 50 C's, and then the rest. So that's not bad. That's pretty good. So, and there's only like 20 of the rest. So that's pretty good for me. I'm usually you know. So I think the SI sessions help. I think a lot of the stuff that the in-class practices seem to help a lot of people. Some people have come to my office hours. Thank you. That was fun. But we're going to continue on with our review, and then we have one more activity here. I'm going to do it. The activity is going to be learning your reactions backwards and forwards and doing a couple retrosynthesis. You can download this off of Canvas. It has the answers on the last page, so don't go to the last page just yet. We're going to do that after we finish the review. So to continue on with the review, we learned a lot in this last couple chapters, and our next exam on Monday will be over 8, 9, 10, and 11, okay? So this slide right here, which, why aren't you displaying? Oh, because I'm not plugged in, that's why. We can't see my slides because I haven't plugged the HDMI cable in. Let's see. Okay, I can see, they can see. I stopped sharing, I'll have to share again. Stop sharing. Share my screen. There. Come on. There it is. All right. Yeah. Okay, so we're recording and sharing my screen here. So this is, okay, this right here is kind of a summary of a lot of the reactions we're going to be taking on the exam on Monday, May 2nd. Monday, May 2nd. Anyway, so this is a good way to think about, you know, starting with all the same materials here, we can make a whole bunch of different functional groups. And so recognizing which functional groups you can make for different things, for example, an ether here, an alcohol here, an epoxy here, a diol here, those are all functional groups that you want to look for. A dibromo compound is different than a monobromo compound. And then you have selectivity on where that bromine goes, depending on which reaction you use. So those are the things we want to look for when we're talking about these things, okay? So, so I'm going to go back up to chapter 10, continue our review on chapter 10, and remind you that the radical polymerization is just those same 3 things happening over and over and over again. Initiation, propagation, and termination, where propagation gets it where it's always head to tail. This is the new bond formed right here, the new bond formed right here in each of these. That one, that one, that one, etc. And so, but they can also do it anionically or cationically. We can do it with a carbocation, which will generate another carbocation. And it'll keep going and going and going because it's going to generate it at that same location. The anion is going to be here, the cation is going to be here, and it'll do that same kind of chain polymerization. So let's think about the structure of our carbocation, right? It's sp2 hybridized with an NP orbital. The radical is sp2 hybridized with 1 electron in the p orbital. And the sp and the anion is sp3 hybridized with 2 electrons in the hybridized orbital. But it's got 2 electrons, and therefore it makes it nucleophilic, and therefore it will continue the polymerization. All right. So let's go back to alcohols. Okay, we did it. We formed alcohols in 2 chapters, technically 3, because we formed them in chapter 6 using nucleophilic substitution with hydroxide. We also did it with a weak, like with water. We could do it with water if it was tertiary substrate. Okay. Or in chapter 8, we found we could add water across a double bond with a acid, with an acid catalyst, or we could do it a couple other ways with mercury and or boron, right? And so then in chapter 11, we learned that we can do the other reactions like the esterifications and etc. So let's review those things real quick. So we have in chapter 6, we did it this way, but in chapter 11, we made the ethers, and we can make unsymmetrical or symmetrical ethers using that same reaction. It's all SN2, because there's only 5 things that can happen in a mechanism, and that's one of them. Attack of a nucleophile, electrophile attacking a nucleophile, etc., to make a new sigma bond. Okay, so the Williamson ether synthesis has a specific pattern you want to use. You want to use it where you have the primary or secondary alkyl halide, and whatever the alcohol is, it doesn't matter whether it's primary, secondary, or tertiary. It's still going to be nucleophilic enough with a primary alkyl halide to do substitution. So you should be able to get that substitution to go. So you want to make sure that you have that reaction going in the correct direction. Okay, now ethers don't do much because they're pretty stable, but if you hit them really hard with 2 equivalents of acid, they will open up and give you 2 equivalents of an alkyl halide, okay? And the oxygen goes away as water, okay? You're not gonna break it up into an alcohol, and that, because once you have that much HBr in there, it can actually sit there and substitute off the alcohol and produce another alkyl halide. But the more important reaction is the epoxy reaction, okay? We have 2 mechanisms. It wants to open up because of ring strength, okay? And if you have a good nucleophile, that nucleophile is going to go on the less sterically demanding side because it wants to do it fast. But if you add acid, now you're turning it into an acid-base reaction, so it slows it down and it's going to attack the more substituted side. Same material, 2 different mechanisms. Good nucleophile, you go for the sterics, you go for the less hindered side. Poor nucleophile, in the presence of acid, you go for the more substituted side. All right, this should be a really familiar because we just did this, okay? Know how to make alcohols into better leading groups, okay? There's a bunch of ways to do it. Turn them into alkyl halides. We have a bunch of different reagents that do this. But remember, when we have a primary alkyl halide, when we have a primary alcohol, we have to use zinc to do HCl because chlorine is not nucleophilic enough. I mean, is not strong enough to do that attack. Remember, it goes by size as you go down. So iodine is more nucleophilic than bromine, which is more nucleophilic than chlorine. By the time you get to chlorine, it really doesn't work very well, unless you add a Lewis acid catalyst. And what did the Lewis acid catalyst do? It made oxygen a better leading group. All right. So let's see how to make epoxies. There's 2 ways to make them. You can take a halohydrin, which is something with an alcohol on one carbon and a halogen on another carbon, and just do the Williamson ether synthesis within the 1 molecule. That's a good way to do it. The only reason it works is because it's so close together and it has lots of opportunities to overcome the ring strain to form that ring. But the better way to make it is with a per acid. A per acid has 1 extra oxygen in there. And the most common one is metachloropurbenzoic acid, MCPBA. So that will be probably seen on a bunch of stuff. Okay, so that's all the review on the reactions from 1 through 12. And now I'm going to hit chapter 9. Okay, and well, FTIR, NMR, spectroscopy, and that. Okay, so be able to identify where your functional groups are. That's going to take you a long way to identifying your compound. Okay, make sure you know the shapes of these peaks right here. Alcohol has 1 shape, carboxylic acid has another. So make sure you know those. Know that how many peaks you have on nitrogen when you have how many hydrogens on there. So that's important. Okay, NMR, we've done a lot of exercises on this, but I still think it's important to remind you that it's the number of spins, the intensity or integration of the signals, I'm sorry, number of signals, position of those signals, and that relative position does not change for carbon or proton NMR, and the spin-spin coupling. Of course, in carbon, all we care about is shift and number of peaks, number of unique carbons, okay? The shift gen trends for our, kind of knowing which zones you're in, next to an alkene, next to an oxygen or halogen, next to on an alkene, phenol, benzenes, and then of course our aldehydes and carboxylic acids as we move down in this direction here. Now note when we look at carbon, it's about the same. We have a little bit wider range here, but all of our halogen, nitrogen, and oxygen stuff is right here in this zone here. We have our triple bonds, and then we have our double bonds way up here. Our carbonyls bonded to an electronegative atom, and then our carbonyls not bonded to an electronegative atom. So the trend is similar. You just need to kind of rack and stack them that way. Sometimes it will do on some of the, like on the quizzes there, I'll tell you what kind of carbon this is. This showed a doublet or a triplet or a quartet. And so you'll know which is which right there. Oh, yeah. All right. So don't forget the N+1 rule, okay? Find the number of hydrogens within 3 bonds. 2 bonds is okay. So when you have alkenes, you can do 2 bonds. And add that number +1 to get your splitting right there, okay? And remember that signals don't split through oxygen or nitrogen. And that you can actually, if they're really close together, you might have a whole bunch of stuff there. You might have 5 protons and that's 2 overlapping signals. Hopefully that's not something I'm going to give on a test, but just want to know. And then you can actually do something really fun is an experiment where if you think you have an alcohol and you think where the alcohol peak is, you can add deuterium to that. And guess what? Deuterium is invisible at that frequency. And actually it ends up being that OH peak will go away. And so you can see that because it exchanges very quickly because it's the most acidic proton. All right, so let's see. The last thing is the 4 most important things about mass spectrometry, which is the molecular ion peak, the base peak, relative abundance, and fragmentation, but also the nitrogen rule. So that's the 5th thing you need to remember. And the 6th thing is the M+2 isotopes, M+2 isotopes, particularly for bromine and chlorine. Okay, and that is that's all you need to know. Okay, so let's do multi-step synthesis exercise. All right, so this last one, this again is posted. The answers are on Canvas somewhere, but I wanted to hit this one more time to kind of reinforce how you should be studying your reactions from your reaction table. Okay, so this product only appeared once in chapter 6. So I wanted to remind you that this is an SN2 reaction where we used nitrogen as a nucleophile. Okay, so this is a retrosynthesis. We want to create this amine, and it was in chapter 6. Go look, it's one of the last pages in chapter 6. And we're going to make this amine from cyclohexane. Okay, so cyclohexane doesn't do much, so we're probably going to have to back it up and functionalize it. And since I told you it was an SN1 reaction, an SN2 reaction, we're probably going to want to functionalize it with something like bromine or chlorine. Okay, so a retrosynthesis to get to there, we'll probably want to back it up to get somewhere where there is a bromine or a chlorine here. I'm going to put a bromine. And then we're going to attack that with the nitrogen nucleophile. Okay.
Where's that?
It's under resources. It's called Multistep Synthesis Exercise. Oh, I'll publish it after class. Just take good notes. Okay, sorry, thank you. So why are we attacking with ammonia and not sodium amide? Sodium amide would have a negative charge, right? But sodium amide is a very strong base. So sodium amide is going to, like in the forming of an alkyne, it's going to dehydrohalogenate this. It's going to act more as a base than a nucleophile, and therefore it's going to the amine here by itself, the ammonia by itself, is a decent nucleophile. So it's going to act as a nucleophile, but not a base. It's not a strong enough base to dehydrohalogenate. So it's going to act as a nucleophile.
Does that work for any weak base or just for
nitrogen? No, nitrogen does it. Oxygen and like water and alcohols, which is the oxygen version of it, are weaker and poorer nucleophiles. This is a pretty decent nucleophile just by itself. Okay, so that means in our starting of it, we're going to have to figure out how to do that. And we figured out how to do that. So let's see, we're going to start out, how can we get a bromine on a cyclohexane?
Radical reaction.
Yeah, so we're just going to do bromine with peroxides. And that's going to give us our cyclohexane with a bromine on it. And then we're going to do this in a solvent, just acetone, doing a polar aprotic. So, because we're trying to force it to do substitution, and then ammonia. And that's going to give us our
there's the reaction backwards.
So this is the retrosynthetic strategy this way. This is the reaction that we had to design from it. So this is what we're trying to figure out how to do, and this is the actual how we did it. Okay. So the key steps here are, this is just an SN2 reaction. This is a good radical reaction. It's one of the few ways to functionalize your hydrocarbons. So you got to know that reaction. Okay. All right, questions on this multi-step? Yeah.
When the ammonia substitutes with the bromine, what deprotonates it? Is it just another NH3 molecule?
Well, when it oh, interesting. When it first goes on there, we end up with a nitrogen with a positive charge, and it has 3 hydrogens on it. Okay. So then this is really how it forms. And then something in the reaction, in this case, either another equivalent of ammonia or the bromine can act as a base to pull off one of those hydrogens to get it to the amine. But remember, when you're attacking with a neutral nucleophile, you get a charged intermediate. When you attack, we made ethers with alcohols. It made a charged oxonium cation, and then we had to lose a proton to get to our deprotonated state. Okay, and that's what's happening here. Okay. Good question. All right. Okay, so let's do that again. We have to make this from acetylene. So let's count our carbons here. 1, 2, 3, 4, 5, 6 carbons. And we have 2 of them. So we need to have at least 3 equivalents of acetylene. We're going to react with it to do something, right? So let's see, what would be a backup step from here? How do you get a tetrabromo compound? Halogenation of acetylene. If you have acetylene right here and you brominate it, and you have two equivalents of bromine, it's going to add once, then it's going to add again. It's the only way to get a tetrabromo compound. So it's a really, really interesting way to do it. So that means we had to make this right here. So we had to make that from acetylene, and we know that when we have acetylene, we can take one of the hydrogens off with sodium amide and use it as a nucleophile. Okay, so if we're using it as a nucleophile, that means we have to have something that looks like this. Because if we did that, attack this with a nucleophile on one side, we'd get half of the molecule. And if we did it again on this side, we get the other half of the molecule. Total of 6 carbons. Okay, so we're allowed to start with acetylene, so that's good. So we know how to get to here, but we need to make this. So how do we make that? So we want a bromine on there, but we want an alkene. If we just added HBr across it, you would get that. That's not exactly what we want. Oh, but then if you hydrogenated that, you would get that. So let's put it all together. We know how to get to this fragment, which is needed for this step, and from acetylene. And we know we can use acetylene in this step to get to there. So let's put it all together. And start here. So I'm going to start with acetylene here. And we're going to go and we're going to do HBr. And going to get that. And then we're going to go hydrogen with palladium. And we're going to get that. Then we're going to go this way with sodium.
That's hydrogen with iridium.
Palladium. Catalytic hydrogenation. It takes alkenes and alkanes, alkynes all the way down to alkanes. Let's see. So that's to make that compound here. It's a bromine right here. So that means we're going to do step 1. We're going to have acetylene plus sodium amide. Step 2, we're going to have the ethyl bromide. And then we're going to do that one more time to the other side. And to another equivalent there. And that's going to get us to here. Okay. So that means the last thing we need to do is 2 equivalents of bromine. Okay. See how knowing the reactions backwards helps you with retrosynthesis. Okay. I'm going to skip that one for right now. Now we're going to do fill in the reagent. Okay. Fill in the reagent. So we have an alkene going to an alkyl halide. And our alkyl, and our halide is bromine. So we're looking like we're adding HBr across there. But which type of HBr reaction do we use? Do we use the one with peroxides, or do we use the one without peroxides to get the bromine on that spot? Without peroxides, because you want the bromine on the more substituted side, because you wanted the hydrogen on the other side. So all we need is HBr, no peroxides. Okay, but then look what we did. We just made another alkene. But this alkene is a more stable alkene, because it's a trans alkene that's an internal alkene. So that's why we want to do it. So what do we do now? We have alkyl halide. We need to make an alkene. So we're going to boil it in water, right? That's not it. Not it. So let's just ETOH and ETO alkoxide. Dehydrohalogenation, remove HBr. Okay, so see how knowing it, the reagent or the change, look for the change and then figure out what the reagent is. Okay, so let's, ooh, there's lots of changes in this one. So it's the first one. We're going from an alkene to an epoxy. We have a way to do that directly.
MCPBA.
MCPBA, little m, CPBA, metachloroperbenzoic acid. And then what did we attack it with to make that crazy looking thing? Got to go all the way back to chapter 6. We attacked it with S-, and oh, it's got a methyl group on it. So we made a good nucleophile out of our sulfur compound, and because they're both substituted one way, and we don't have any acid, so it's going to just open this way. This group is slightly bigger than this group, so it'll probably go to the less hindered side, and it opens it up. And we're going to do it in probably a solvent that like THF, a polar aprotic solvent. We don't want that epoxy to get protonated. So you'll see a lot about, you know, different solvents on an exam. Just figure out whether it's polar protic or polar aprotic, and then you'll know why it's there. Okay. All right, let's do this one. Oh, this one's fun. I was going to do this as a retrosynthesis, but it has a rearrangement in it, so I thought I'd be nice. We'll do it this way. So let's see. How can we convert an alcohol, primary alcohol, into an alkyl halide? Specifically the chlorine. We actually have three different reagents we can use. Anybody? Zinc chloride with HCl, that's one.
Thionyl chloride.
Thionyl chloride, which is OSCl2.
Something PCl3.
PCl5. Now, what if we wanted to have a better leaving group? Instead of the chlorine, what would we do?
PBr.
No, if we wanted something other than chlorine there, we wanted to just make oxygen a better leaving group. We turn it into a tosyl group, and that would do the same thing. Okay. All right. So, but we have the chlorine, which means all we have to do is add a good base. ETOH with ETO minus right there. It's a primary, so that might work. It also might get a little bit of substitution because it's a primary alkyl halide. So we should probably actually do a little bit better, do the T-butyl with the T-butyl alcohol. That would guarantee that there is no substitution. Okay. Now, once we have this here, how does it rearrange like this? What are we doing? Well, let's see. If we're going to add HBr across here, because we only have one bromine, so we probably are adding HBr. Let's see, the hydrogen's going to go here and giving us a carbocation there. And then that's going to do the 1,2 ring expansion. And then we'll still have our carbocation there. And then the bromine comes and attaches it. So we had the same number of carbons, but we had that rearrangement to deal with. Okay, so now let's do this one. So we have an ether on there, and then we have 2 carboxylic acids. And I say we can start from an alkene. We're going to start from cycloalkene. cyclohexene. Okay. So I think we need to get, well, we can actually just cut the ring apart and get to the dicarboxylic acid that way. And that would be easy, but that doesn't get us our ether on here. So we have to find a way to put an ether on there. We know we can make an ether in a couple different ways. When we have alkyl halides, we can, or an alkene, we can do, we can add across the double bond in the presence of like the hydrohalogenation, I'm sorry, the boronation in the presence, no, not that one. Mercury, you can do it where you have it with an alcohol and you can add an ether, or in the case of acid catalyzed, you can have an ether. However, if we do that, we're going to add it across the double bond goes away. Okay, so we need to find a way to have a leaving group that is next to a double bond, either here or here, next to the double bond to do our substitution on first. Then we can break the ring in half. Okay, so gosh, do we have some way to functionalize here and here? Yeah, we do. We have a reaction with bromine and peroxides. This allylic position is more reactive than the other positions, and therefore it will create a bromine here. Now, this is a good leaving group, and so we just have to attack it with a good nucleophile, bromine here. And oh, it's going to be actually the meth oxide. What's the problem with this possible synthesis? Some of your product is going to be the diene, because methoxide can not only act as a nucleophile, but it can also act as a base. So let's put it all together. Okay, let's start with our cyclohexene. Let's draw it a little bit better than that. There we go. Cyclohexene, we're going to do bromine in peroxides, and we're going to get selectivity. It's going to be next to the double bond, and the double bond is still there. And then we're going to attack it with Me in methanol. And that's going to give us OMe with our double bond still intact. And then we're going to clip that double bond with potassium permanganate and base and water. And that gives us our product. Yes.
Is potassium permanganate the one that can make carboxylic acid?
Correct.
Okay. So ozonolysis is the
Ozonolysis can make carboxylic acids too if you run the reaction, if you work the reaction up with water and base, it'll make carboxylic acids as well.
Okay.
But the only way to make aldehydes is ozonolysis with dimethyl sulfide, a reducing environment. Okay, so like I said, the answers are on the last slide if you want to go through it yourself and try to do that. Okay, questions on retrosynthesis. Okay. See, I like to sum up with retrosynthesis and not do it actually in the chapter where it first appears, because we have so many reactions now. We can convert our carboxylic acid, we can convert our alcohols to halides, and our halides to alkenes, and our alkenes to alcohols, and our alcohols back to alkenes, and our alkenes to epoxies. So we can have so many reactions at our disposal now that we can do a whole bunch of the retrosynthesis stuff. Okay. Any questions? Okay. That is all I have for this. I will post the video online. And let me go ahead and stop sharing and stop recording. And if people have questions, you can come up and ask. All right. All right. Oh, by the way, don't forget, take your quiz at home if you haven't already, please. And exam on Monday, May 2nd. No, I haven't got them from the SI section yet. All right, well, I'm gonna stop recording.